Let's take a look at the remaining problems on the 3.6 Achieve homework assignment. There's several of these problems where it's asking you to find the equation of the tangent line. Number 15 gave me a problem y is equal to 26 times the group sine theta plus cosine theta. And it was asking me to find the equation of the tangent line at theta equals pi over 3. Okay, so I know in order to find the equation of a line, I first need to find the point. So I can say all I need to do is plug pi over 3 in for the value of theta and solve for y. I get 26 times the sine of theta plus the cosine, the sine of pi over 3 plus the cosine of pi over 3. I know that at pi over 3, the sine function, the y value in the unit circle goes up to the square root of 3 over 2. At that point, the cosine is 1/2. So now I have 26 times the group, square root of 3 plus 1 all over 2. Since that's common denominator of 2, I can say, well, then I have square root of 3 plus 1 divided by 2 times 26. That means it's 13 times the group, the square root of 3 plus 1. Now I have my y value at the point of interest for theta. Now I need to know the slope. Well, the slope is just going to be theta equals pi over 3 evaluated into the derivative. So the derivative here, I could think of this as the product rule, but the derivative of any constant is 0. So I'd say, well, derivative of the first is 0 times the second plus the first 26 now times the derivative of the second. Derivative of that second, derivative of the first portion of it, derivative of sine is cosine. Derivative of cosine is negative sine. So the derivative of that second term is cosine x minus the sine of x. Now, once I have the derivative taken, I evaluate it at pi over 3. And I've already said that we know that the cosine of pi over 3 is 1/2. The sine of pi over 3 is the square root of 3 over 2. This time, though, we're subtracting that sine of pi over 3. So my inside becomes 1 over 2 minus the square root of 3 over 2. Once again, this 2 can cancel with the 26, and it's just going to give me 13 times the group, 1 minus the root of 3. Now, this is my exact value for the slope, my exact value for the y value at that given value of theta. So then I can say I'll take that slope, I'll take that point, plug it into my point slope equation for a line. So I do y minus y1, my y1 value right here, equals the slope, here is my equation for the slope, times x minus x1, technically it's x minus theta 1, or theta minus theta 1, I'll have the minus pi over 3 there. Now, the only thing it's wanting you to do, because it's wanting you to keep the answers exact, don't worry about distributing this through that group. Just move the plus 13 times the square root of 3 plus 1 over. Now, when I worked this problem, I actually had Achieve tell me my answer was wrong 2 or 3 times. I'm like, I am not wrong. What's the matter? It's because I'm so used to putting my point slope equation, y in terms of x. But please remember, your independent variable in this problem is theta. So all you have to do, even if you do like I did and put it in terms of x, is right after you do that, just say, oh, well, the independent variable is theta, switch that out for theta. I had to enter my answer several times before I figured out what I was doing wrong, not putting the independent variable theta in my final answer. Okay, number 16 here. Again, same idea. It's giving us an equation, and it's wanting us to find the equation of the tangent line at a given value of x. In this case, it's just at x equals 0. We know the point is going to have the y value when you plug 0 into the equation. Gives me 13 e to the 0 cosine of 0. We know any number to the 0 power is 1. We also know the cosine of 0 is 1. So y evaluated at 0 is just 13 times 1 times 1. I get a 13. So now I have my point, the ordered pair 0, 13. I need the slope. Well, the slope, I can take the derivative of this equation. When I take the derivative, it will have to be taken with the product rule, because I have the differentiable function 13e to the x times the differentiable function cosine x. Its derivative is the derivative of the first, which is Derivative of any exponential function is that exponential function times the second plus the first, 13e to the x, now times the derivative of the second, derivative of cosine negative sine. So now once I get to this for my correct derivative, I would prefer to go ahead and factor that. And you could say, well, both terms have the common factor of 13e to the x. When you factor that out, you'll be left with cosine x minus sine x. So this is my simplified factored first derivative. Now, in order to find the slope at the point of interest, you simply evaluate this derivative at the point of interest, 0. So when I plug a 0 in here, I would have 13e to the 0 times the group cosine of 0 minus the sine of 0. Well, I know that the cosine of 0 is 1. So yet again, I'm going to have 13 times 1 minus 0, 13 times 1 times 1. I'm not only getting 13 for the y value, but I'm getting 13 for the slope. So I can say my slope is 13, my ordered pair is 0, 13. Plug that into your point slope formula. You get y minus 13 is equal to 13 times x minus 0. That would give me 13x plus 13 for my final formula there. Pretty straightforward there. That one's, once you get down to the equation, that's one of our easier point slope equations. For the next one here, number 17, it had me look at, again, a function that's going to require the product rule to take the derivative y equals 3e to the t times 1 minus the cosine of t, and it's wanting the equation of the tangent line at t equals pi over 2. Okay, so I first need to find the point. Evaluate your function at pi over 2. That's going to give me 3 times e to the pi over 2, which I know is an extremely irrational number. So I'll just leave it like that, times the group 1 minus the cosine of pi over 2. Please remember the cosine of pi over 2, that's asking you what's the x component of the unit circle when it moves straight upward. Well, it's 0. So this is just going to be the group 1 minus 0, so a factor of 1. We're just going to get 3 times e to the pi over 2 for our y value. Now I need to find the slope. So I can say, all right, then you need the derivative. Derivative of the product is the derivative of the first term times the second plus the first term times the derivative of the second. We know derivative of 1 is 0. Derivative of negative cosine is a positive sine. So now this is my correct derivative. I always think it's better if you'll factor whenever possible. I can easily factor this. Both terms have a common factor of 3e to the t. When I factor that out, I'll be left with 1 minus cosine t plus sine t in my remaining factor. Now I need to evaluate that first derivative at pi over 2. So I can say, okay, then I'll still get 3e to the pi over 2 times the group 1 minus the cosine of pi over 2, which I know is 0, plus the sine of pi over 2, which I know is 1. So this group here is just going to give me 1 plus 1. That's going to be a 2. 2 times 3e to the pi over 2 gives me 6e to the pi over 2. So now I have my slope. I have my point. I'll say, well, my point is pi over 2, comma 3e to the pi over 2. My slope is 6e to the pi over 2. I plugged that into my point slope formula. This time I remembered your independent variable is t, so instead of m times x minus x1, it's going to be m times t minus t1. So I get y minus y1 right there equals your slope times t minus t1. Your t1 value is your independent variable in your ordered pair, pi over 2. So then we can say, well, we'll just leave the right-hand side alone. You don't have to distribute through. It's better if you don't. And then add 3e to the pi over 2 to the right-hand side. You'd have your final exact correct answer. Now, the next few problems actually get pretty quick. It's wanting us to simplify some expressions, and notation here is an important thing. For number 18, it's wanting you to simplify the fraction where you're only taking the derivative in the numerator. This is telling me take the derivative with respect to x of 8 cotangent x, take that answer and divide it by the cosecant squared x. Okay, so the derivative with respect to x of cotangent, please remember derivative of cotangent is negative cosecant squared. So the derivative with respect to x of 8 cotangent is going to be 8 times a negative cosecant squared. Now, I'm dividing that by the cosecant squared in the denominator. Clearly, my cosecant squareds would cancel, and I would have 8 times negative 1. Technically, your denominator would be a 1, and you could say, well, 8 times negative 1, that's just going to simplify to be negative 8. For the next one here, it's asking me to take the derivative with respect to x of 7 cosecant x, take that answer and divide it by cosecant cotangent. This is very similar to the last problem because you're supposed to remember, well, I know that the derivative of cosecant is negative cosecant cotangent. So the derivative with respect to x of cosecant x is negative cosecant x cotangent x. The constant just stays along with it. And then when you say, well, all right, when I simplify that with the denominator, the factor of cosecant and cotangent would cancel. You'd be left with 7 times negative 1 for your final answer of negative 7. Now for the next one, number 20. It gave me a function f of theta, and it simply just said, find the derivative. F of theta is going to require the product rule. It's 2 theta times the sine of theta. So I can say, all right, product rule says derivative of the first, 2, times the second, sine theta, plus the first, your 2 theta, times the derivative of the second, derivative of sine is cosine. So I have my correct derivative taken. I just wanted to go ahead and simplify it. Oh, no, sorry, not simplify that. I needed to take the second derivative, not just the first derivative. So yes, in order to find the second derivative, you needed the first derivative. But now I'll take that derivative of the first derivative to get to my second derivative. Then I'll simplify. So derivative of this term, well, derivative of sine is cosine, so the derivative of 2 sine theta is 2 cosine theta. Now, here's the slightly tricky part. Whenever you're looking at how to take the derivative of this derivative, the first term, no problem. Derivative of sine is cosine. The second term, you need to understand, you have to take that term's derivative with the product rule because it's a differentiable function times a differentiable function. So I'll say, okay, well, it's derivative of this plus the derivative of this is going to be derivative of the first term, 2 times the second, plus the first term, 2 theta, times the derivative of the second, derivative of cosine is negative sine. So now, once I get this answer, I can say, well, my answer has 3 terms. What could I pull out amongst all those terms? And actually, before I even worry about that, it doesn't really have 3 terms because I see the first 2 terms are like terms. 2 cosine theta plus 2 cosine theta is going to give me 4 cosine theta. And then I would have, remember, this is a multiplication of a negative factor of negative 1, so that's going to make this minus 2 theta sine theta. And at that point, I could have factored out a 2, but I decided not to do that. Up next, you have an equation in which you're asked to find higher power of derivatives. We're looking for the third derivative in this case. So my original function is 9 tangent x. So I can say, well, okay, the first derivative, we know that the derivative of tangent, or we should know, derivative of tangent is secant squared. So the derivative of 9 tangent is 9 secant squared x. That's a problem because I need to further take the derivative of that. And I don't know how to take the derivative of powers of trigonometric functions yet. So the only thing I can do while sticking with the techniques of differentiation that I know at this point is to just say, well, secant squared x is secant x times secant x. Now when I take the second derivative, I'll be using the product rule. I'll say, well, this is my first function times this is my second function. So the product rule is going to say, well, the derivative of the first, derivative of 9 secant, is going to be 9 secant x tangent x times the second, plus the first times the derivative of the second. And of course, again, derivative of secant x is secant x tangent x. Now, when I simplify this, you could say, well, why don't you just write this as 18 secant squared tangent x? Because they're this term and this term is the exact same thing. Well, I certainly do want to add them together, but just as in the last case, I need to leave this as secant x times secant x as opposed to writing it as secant squared x. And like I said in red here, it's because I need to find the third derivative. If I didn't need to find the third derivative, I would have just left that 18 secant squared x tangent x. But since I don't know the chain rule yet, and I need to take the third derivative, I'll have to leave my function out like this. Now, the gorgeous thing about this, hopefully you see, is that this is going to create a 3-term product rule. You have the differentiable function 18 secant x times the differentiable function secant x times the differentiable function tangent x. So I can say, okay, and I'm showing my work here. You would not have to show this next step. I'm just trying to show you my thinking. It's derivative of the first term times the second times the third, plus the first term times the derivative of the second times the third, plus the first term times the second term times the derivative of the third term. Now, derivative of 18 secant x is 18 secant x tangent x times secant x tangent x. That was already there. We know that the derivative of secant is secant tangent, so I have my first term times the derivative of the second times the third. Here I have my first term times the second term. Now, times the derivative of the third term. Well, derivative of tangent is secant squared. So now I get to this point and I say, oh, I know my derivative has been taken and it's been taken correctly. Do I have a way of writing that more efficiently? Oh, you bet. You know that you can factor out an 18, and you can also factor out at least a secant squared amongst all 3 terms. So I would recommend factoring out an 18 secant squared x. But now when you do that, please notice also your first 2 terms were the exact same thing. They were 18 secant squared x tangent squared x. So I have 18 secant squared x tangent squared x plus 18 secant squared x tangent squared x. That would give me 36 secant squared x tangent squared x. When I factor an 18 out of that, I'm left with 2 tangent squared x. And then when I factor an 18 secant squared x out of the last term, that's just going to leave me with the remaining secant squared x factor left there. Fully factored final fantastic form of the answer. So we have our first derivative, second derivative, and third derivative. Now, for number 22, it was asking for the 24th and 25th derivative of the negative sine of x. Well, what you're supposed to remember, any cyclical function is going to have a recursive pattern for its derivatives that's going to cycle around and start being the same thing over again. So I just go through that and I can say, well, I know that the derivative of sine is cosine. So the derivative of negative sine is negative cosine. The derivative of negative cosine would be positive sine. The derivative of sine is cosine. And then I know that the derivative of cosine is negative sine. So here's where it cycles back around to itself. And so you're supposed to say, okay, what am I supposed to draw from this? You're supposed to understand that every 4th order of the derivative is going to go back to the original function. So then I can say, well, all right, then the 5th derivative, it's the same thing as the 1st derivative. It is negative cosine x. Well, what's the 24th derivative? You say, well, you've just taken 4 derivatives 6 times, so the 24th derivative is going to be the exact same thing as the 4th derivative. And all you have to do is you divide this into this and say, well, it divides evenly. Then it's the exact same derivative. And you'd say, well, the 24th derivative is also the negative sine of x. Now, if it's asking for the 25th derivative, you could take 4 divides into 25. It goes 6 times with 1 left over, which means since there's 1 left over, this is the same thing as the first derivative, and I get my negative cosine. Now, for the last problem, it asked where the curve given would have horizontal tangents. And I know it has a horizontal tangent. Remember, the tangent line is going to be horizontal whenever a function has a 0 slope. Horizontal lines have a 0 slope. So when it's asking where will it have horizontal tangents, you just say, well, it can only have any horizontal tangent line if the slope of the curve is 0. So I need to set my derivative equal to 0. So as soon as you see that, you just say, saying take the derivative, set it equal to 0. So I look at my equation, I take the derivative, and I do so using the product rule. I say derivative of the first is cosine times the second plus the first times the derivative of the second, derivative of cosine negative sine. So for my derivative, I'm going to get cosine squared x, and it will be minus sine squared x. I need to set that derivative equal to 0 to find where it will have horizontal tangents. When I do this, I just move the sine squared x over to the other side, and I said, well, this is just asking me, when is the square of the cosine function equal to the square of the sine function? And it specifically said on the interval between 0 and pi. And that was easy because I know that the cosine and sine are equal to one another at the midpoint of each quadrant. At least they're that they could be opposites of one another, but they're the same absolute value. So I can say at pi over 4, they are exactly the same. They're both the square root of 2 over 2. At 3 pi over 4, obviously they're opposites of one another. The cosine is the negative square root of 2 over 2. The sine's the positive square root of 2 over 2. But if you square those, it's the same thing. So you can say it's at both pi over 4 and 3 pi over 4. That will be the values at which your original curve will have horizontal tangent lines. And so in this case, you just had to write it as pi over 4 comma 3 pi over 4. It didn't want the 2 out individually like that. All right, this should help you with the section 3.6. Absolutely fun stuff. Please let me know if you have any questions. As always, I'll be happy to help.